So I will talk about some functional transcendence conjecture. Let me explain first the setting, the motivation. So the plan for the talk will be first I will give some motivation for this conjecture, and then after that I would like to introduce a general setting that one can call bi-algebraic geometry and explain what the Axing-Demand-Weierstrass conjecture is about. Then I will try to explain some parts of the proof of the main result. Okay, so the motivation comes from Hodge theory, at least for me. And I will start recalling some basic stuff that Christian already explained yesterday, namely Hodge locus. So the basic setting is the following. You start with S smooth quasi-projective, and you give yourself polarized Z variation of Hodge structure on S. So that's the data. And as Christian explained, I mean, the most interesting situation is the case where you look at the smooth projective family of S, and you look at the family of cohomology in certain degree I. Take the primitive one for simplicity. Okay, so that's the setting. And what is remarkable in this setting, as Christian explained yesterday, is that once you have this data, you get some geometric object contained in S, namely the Hodge locus. So this is a collection of points in S where you have exceptional Hodge classes that appear in the fiber or in some tensor power of the fiber. Okay? And Christian recalled us yesterday the basic result about this locus, that this is a countable union of algebraic subvarieties of S. Okay, so the main motivation for this talk is trying to understand this locus. More precisely, let's take the following definition. I recall a special subvariety of associated to this datum. It would be an irreducible stratum of this Hodge locus. Namely, you take all the components, you take all the intersections, and well, you call stratum just an irreducible component of such an intersection. Okay, and the basic question is try to understand the distribution in S of special subvarieties, especially special points. So special points are just special subvarieties of dimension 0. So in some sense, these are the points where you have the most Hodge classes appearing in this tensor product. All right, so let's take a very simple example to motivate the talk. So for S, for your base, you choose the modular curve. So it's just the quotient of the upper half plane by SL to Z. And by the J function, this is isomorphic to C. So it has canonically an algebraic structure, and this is just C. Okay, so this is a moduli space of C elliptic curves, and you think of these elliptic curves as being weight 1 polarized variation, the Hodge structures. Okay? So the correspondence is just to a point in the upper half plane tau, you associate the elliptic curve C divided by Z plus tau Z. So now what is a special point? So it has to be an elliptic curve, or if you want a weight 1 Z Hodge structure, such that there is some special Hodge classes appearing in a tensor product of this Hodge structure. And in fact, well, obviously, elliptic curve, the Hodge structure is weight 1, so you don't have any Hodge class. But if you look at the endomorphism, this is a weight 0 Hodge structure. And so you have special Hodge classes exactly when tau is imaginary quadratic. In this case, the elliptic curves acquires complex multiplication by Q of tau. And so this gives you special Hodge classes in the endomorphism. So if you want to understand the distribution of special subvarieties, in this case, this is very simple. I mean, you have only points. And the basic fact of life is that special points are dense in Y0 of 1 in C. And just because these imaginary quadratic guys are dense in H. Okay? And this is true even for the usual topology. All right, so there is no question about that. We understand everything. Let's go to the next example. Let's just take a product of two modular curves. So as an algebraic variety, this is just C times C. And this is the moduli space of pairs of elliptic curves. Now, what are the special subvarieties there? Well, for the special points, it's easy to see that they correspond to pairs of special points, so nothing new. And for special curves, well, you have kind of trivial curves. The vertical or the horizontal lines passing through a special point, they will be special, obviously. And you have more interesting ones, namely, you just look at the image of another modular curve. This one, the moduli space of isogenies between the two elliptic curve, and you just forget the degree of the isogeny. Okay. So to an isogeny between two curves, you associate the pair E1, E2, and so you have a natural embedding of this, and it's easy to see that these are all the special curves. Okay, and now you can ask the following question. Well, notice that every special curve contains infinitely many special points. And the basic question is about the converse. So this is a conjecture done by André in '89, that if you take an irreducible curve in C times C, and you assume it contains infinitely many special points, then it has to be special, namely of this form. So this is a very simple conjecture in C times C. Okay. All right, so the problem, if you want to study this is the general problem of the distribution of special subvarieties for any variation of a structure, is that you would like to do that, well, in a universal way, but Griffith's transversality condition for variations of a structure prevents the existence of general moduli spaces. So what I will do in the rest of this talk is I will put myself in a setting where you have moduli spaces, namely in the case where Griffith's transversality condition is empty. And these are exactly the setting where S will be a Shimoda variety. So what is a Shimoda variety? Well, there is a kind of elaborate definition of it. But for me, I will be only interested in basic properties. So from the point of view of complex geometries, these are very simple objects. You start with a bounded symmetric domain in C to the n, right? So just something open in C to the n, which is symmetric in the sense that the group of automorphism is big. It acts transitively on it. And you just take a quotient by the set of integral points for the group of automorphism. Okay, so this will be such a quotient, and this is what I call a connected Shimoda variety. So the important point here is that the subgroup is an arithmetic subgroup, and even congruence, but it will play no role in what I will do later. All right, so this is the basic datum, and this will be our S. So let me give some example of this. So obviously, we already saw some cases, namely modular curves, but you can generalize it in many obvious ways. So the first way is to try to generalize the upper half-plane, which is also the ball in dimension 1, to a ball in any dimension, in which case you get some unitary group acting on this. Another generalization is to consider the case where you take matrices of size PQ, and you ask that they satisfy this condition, where this star is a transconjugate of Z. Okay? And in this case, the group, it's easy to see that the group that acts on this space transitively is PU-PQ, the unitary group of signature PQ. And then probably the most well-known case is the last one, where in addition to this condition, you moreover ask that the matrix Z is antisymmetric. And then in this case, the automorphism group is SP, and you get the usual moduli space of abelian varieties of dimension G. Okay. So these are nice objects and quite natural in many different topics in geometry. Okay, so the point is that there are a few basic facts to understand. First, it's not obvious on this definition as a quotient that that such an S is an algebraic variety. But in fact, there is a canonical structure of a quasi-projective variety over C. This is a classical result of Bailey and Borel, and even over Q bar, and this is due to Shimura and Dolin. So I did not give you the modular definition of such an object. I just told you that this is some kind of moduli space. You have to think modular space of abelian varieties with extra structures. And because of this modular definition, there is a canonical Z variation of our structure on the Shimura variety. And so we are exactly in the setting of we started with. So what is nice also is that you can completely describe the Hodge locus in the sense that you can completely describe the special subvarieties. And you can describe them in many different ways. So there is a nice description from the group theoretical point of view. After all, I define these Shimura varieties as group theoretical objects. And these are just some irreducible components of a translate of Shimura subvarieties. But it will not be important in this talk, so I don't have to define all those terms. That's nice for me. There is a very simple characterization in terms of differential geometry. So what is a special subvariety here? It's just something which is totally geodesic for the canonical metric on S, and which contains at least one special point. So this is, I would say, the characterization in terms of differential geometry. what is the basic fact about this is that those special points, they are Q-bar points, okay, in S, and they are dense in each special subvariety. In particular, they are dense in S. So this is exactly the same picture that the one we had for the product of two modular curves, right? All right. So what is the generalization of the conjecture of André for product of curves is that for any connected Shimura variety, if you take a closed irreducible algebraic subvariety, then if it contains the Zariski dense set of special points, it has to be special itself. Okay. Another way of looking at this conjecture equivalently is to say that if you fix Z, then there are only finitely many special subvarieties which are contained in it, except if Z is special itself. Okay. So this conjecture is essentially due to André and Oort independently. I mean, André was interested in this case of product of curves, and Oort in the case of moduli space of abelian varieties. And well, at that point, it's a good point to note is that there is some formal similarity with the Malin-Mumford conjecture. So let me recall this conjecture, which is a theorem which was proven by Reynaud. You start with an abelian variety. So the abelian variety will play the role of the Shimura variety. And you have Z inside this abelian variety, a closed irreducible algebraic subvariety. And then the question is, how do you meet torsion points? And the answer is that if you have Zariski dense set of torsion points in Z, then Z is a translate of an abelian subvariety by a torsion point. So the similarity is very clear. S is replaced by an abelian variety. Special subvarieties are translate of abelian subvariety by torsion point. In particular, torsion points corresponds to special points in the case of Shimura variety. Okay, so what are the results of this conjecture? Well, with Ulmo and Yafaev, we proved this conjecture under GRH, generalized Riemann hypothesis. And the proof is kind of complicated. We use different tools coming from ergodic theory and also basic results in algebraic and arithmetic geometry. But what I will be interested in today is the remarkable proof of Pila in 2010, where he succeeded in proving the André-Oort conjecture unconditionally under the strong restriction that S is a product of modular curves. But nevertheless, it was really a breakthrough because he introduced a very nice idea, and especially introduced this idea of using some statement that I will call the Axel-Lindemann-Weierstrass conjecture. So this is what I would. So this was basically the whole introduction, and now I will go to the setting of bialgebraic complex geometry. So what is this setting? The idea is that you consider a morphism between two complex algebraic varieties, but you assume this morphism is just transcendental, very transcendental, okay, not algebraic. And then if you are in this setting, you can ask a few basic questions. The first question is, describe what I call the bialgebraic subvarieties. Namely, this will be pairs of y containing x and v, which is the image of y under pi, and I ask that both of them are algebraic under this transcendental morphism. So because the morphism is very transcendental, there should be very few of them. And this should have something to tell you about the geometry of the situation. Okay? So this is the first question you want to ask. And if you are able to answer this question, then you can try to make the following statement. Sorry? Oh, yeah, sorry. This is a typo. Yeah. This is pi of y. Yeah, sorry for that. So what is the Axel-Lindemann-Weierstrass statement? This is a very simple statement. You start with an algebraic subvariety of x, I will say upstairs, and you take its image. So in general, this is not obviously algebraic, but let's just take the Zariski closure of it. And then the claim is that this Zariski closure is bialgebraic. Okay. It is a very simple statement. Yeah, so this means that any irreducible component of the pre-image of this Zariski closure is also algebraic upstairs. Okay. I will give some simple example later to illustrate this. What will be important for the rest of the talk is that this very clear picture, you can also equivalently consider the following equivalent statement. Namely, now you start from someone algebraic in S, take the pre-image, okay? So obviously this pre-image is not algebraic in general, but now you ask what are the irreducible algebraic subvariety contained in this pre-image and maximal for this property. And this, the equivalent statement to this Ax-Lindemann-Weierstrass statement is that this Y has to be bi-algebraic. So let me give simple examples, maybe to illustrate what happens. So we start with the following very transcendental morphism, namely the multi-exponential from C to the n to C star to the n. Okay? And then what are the bi-algebraic subvarieties? So you're asking for a subvariety of C to the n such that the image is also algebraic for the canonical structure in C star to the n. And the answer is very easy. You just have the translate of rational linear subspace in C to the n. And well, this oops. No. Okay. Well, what we will see is that they correspond exactly to special subvarieties in this setting. But so clearly, you take a rational linear subspace here, then it will be mapped to subtorus here, and you allow yourself translations. Okay. And it's easy to see that you don't have any other ones. All right. So what is the Ax-Lindemann-Weierstrass statement in this case? Well, this is the following theorem of Ax, which says that if you start with an algebraic subvariety of C to the n, takes its image under this multi-exponential, takes the Zariski closure, then this is a torus, or a translate of a torus. Okay, let's take another similar example. Maybe some remark here. Why this is called Ax-Lindemann statement is that because this is just a functional analog, a geometric analog of the classical Lindemann-Weierstrass theorem that tells you that if you take alpha 1, alpha n in Q bar, which are Q linearly independent, then when you take the exponentials, then they are Q algebraically independent. Exactly the same statement, but in a functional setting. Okay. Next example is the abelian case. So now for pi, you take the uniformizing map of an abelian variety. So the map from C to the n to C to the n over a lattice lambda. And then what are the bi-algebraic subvarieties? Well, these are the translate of linear subspaces in C to the n covering translate of abelian subvarieties in A. It's also not too difficult to prove. And what is the Ax-Lindemann-Weierstrass statement in this context? Well, this is still a theorem of Ax that if you take Y in C to the n, an algebraic subvariety, and then if you take the image and then the Zariski closure, then any irreducible component of this Zariski closure is a translate of an abelian subvariety of A. Okay, so in these simple kind of nature examples, yeah. No, not necessarily. You have to be a bit careful. This is a weakly special subvariety, so it's not necessarily a torsion point. Yeah, I mean it's just holomorphic, not algebraic. Yeah, I mean no, for sure. So you are looking for nice situations where you have a chance of this. I mean, at least you have to first understand the bi-algebraic things, and usually, I mean, it's not easy at all. So what will be our saying? Well, yeah, maybe it's clear. If you remember the Manning-Mumford conjecture, it's clear that this statement is very close. I mean, it's directly linked to the Manning-Mumford conjecture, right? And in fact, then you notice that once you have this statement, then you can obtain a new proof, because there are many proofs now of the Manning-Mumford conjecture, using this result of Ax as a crucial ingredient. Yeah, of course, but I will come to that. So yeah, I will explain later that what is the main result that you use to prove the Manning-Mumford conjecture using this. And this striking idea of Pila, and originating in his paper with Bombieri. And Pila realized that one also might try to use this kind of bi-algebraic setting and some kind of Ax-Lindemann-Weierstrass statement to prove the Andrew-Hort conjecture. Okay. So what is the hyperbolic Ax-Lindemann-Weierstrass conjecture? So we come back to our setting. We start with the Shimura variety S, and X is our bounded symmetric domain, and we just look at pi, the uniformizing map. So notice at that point that we are not exactly in the settings that I described. Why? Well, basically because This bounded symmetric domain X is not an algebraic variety. But in some sense, it's not a real problem because it has a canonical semi-algebraic structure as a bounded open domain in C to the n. And so because of this, you can just take as a definition that an irreducible algebraic subvariety of X, well, this is just something that we obtain by taking an irreducible component of the intersection of something algebraic in C to the n with the domain. That's it. All right, so this is the next remark, is that this semi-algebraic structure is really canonical. So if you use any other, I would say, natural semi-algebraic realization of X, like as the link suggested, the Borel embedding inside the compact dual, then you get the same notion of algebraic subsets. So it's really a nice definition. And so in this setting, Unmo and Yerfeev prove that the bialgebraic subvarieties in S are exactly the weakly special, namely the totally geodesic subvarieties. Okay? So weakly special just means this is like special, except you do not have to contain a special point. Okay, so now what is the theorem? Well, the theorem is that the Ax-Lindemann-Weierstrass conjecture holds true also in this setting. Namely, you take any algebraic subvarieties in X, take its image under pi, take the Zariski closure, then this is a weakly special subvariety, something totally geodesic. Okay, so some remarks about this result is that for S compact, this was proven first by Unmo and Yerfeev, and then Pila and Zimmermann obtained this result for S is equal to AG, and we then proved this theorem, and Mock is able to relieve, I mean, in higher rank, the arithmetic condition on the group is always satisfied by Margulis superrigidity theorem. But in rank 1, you can have non-arithmetic lattices, but still, Mock is able to give a proof also of this result using purely differential geometric methods. What are the corollaries? Well, the first corollary is that using this theorem, you can obtain new proof of the André-Oort conjecture under GRH. So, well, why are we happy? Well, basically because in our first proof, we use GRH 2 times. And here, we use it only 1. So it's a bit better. And all yes, exactly. Yeah, it was much more serious. So and well, the nice result obtained is also that the André-Oort conjecture holds true unconditionally for for A6 to the n, for any n. So we don't have, I mean, as Peter is saying, the main problem that remains is to have good lower bounds about Galois orbits of special points. And this we can do under GRH, but in general we can do it only in small dimension like A6. So that's the main reason. Okay, so now what I want to do is try to explain the proof of this. Yes, exactly. AR up to 6. So what is the strategy of the proof? Strategy of the proof, well, we put ourselves in the setting of the Ax-Lindemann-Weierstrass theorem. So this means that we have this uniformizing map X to my Shimura variety. So X is my bounded symmetric domain in C to the n. I take a guy which is, let's say, irreducible algebraic in S. I take the preimage. So this is something terrible in the universal cover in this bounded symmetric domain. And then I look for a Y which is algebraic, irreducible contained in this preimage, and maximal for those properties. And what do I want to prove? I want to prove that Y is totally geodesic. This is what I want to prove. And how do I do that? Well, the first step is to prove that this Y, if it is totally geodesic, it will be stabilized by a very big group. Its stabilizer will be big because it will essentially act transitively on Y. So what we have to show, and this is essentially enough, is to prove that there is a positive dimensional Q algebraic subgroup of G that stabilizes Y. If you prove this, then, and this will be the third step in our proof, what is a candidate? Well, you take the following group. Let's look at the stabilizer inside the real points of Y. So this is a priori a Lie group, but you intersect with the Z points. So notice that this set could be finite, and this is exactly what we want to exclude. I mean, if Y were generic, this set is finite, the Zariski closure is itself, and you are not very happy. But the claim is that in this situation, this set is infinite. There are infinitely many elements in the G of Z that preserve Y, and this is enough to create a big algebraic Q subgroup. Okay, so this is the theorem 3, and using classical arguments in Hodge theory, essentially the linear simplicity theorem, then it's enough, if you prove this, that the stabilizer is really big, to prove that Y is weakly special, totally geodesic. Okay. So how do we prove this step? Well, we do the following. First, we fix a fundamental set for the gamma action, for the action of the fundamental group. And then we look at the subset of all the elements in G of R, such that we have this property. So you have this Y, which is algebraic. You translate it under some element of G of R, and you are asking that first, there is still some part contained in pi minus 1 of V, in the preimage of the algebraic guy downstairs. And it is cutting the fundamental set, and we ask that the dimension of this intersection is the same as the dimension of Y. Okay. So what is the remark? The remark is that if there is an element G in this set, then when you translate one under G, well, because of this condition, in fact, an analytic continuation, it will still be contained in pi minus 1 of V, and it will also be maximal irreducible algebraic, because for these conditions, right? Because the action of G is algebraic. And so what we have to do is basically to prove that this set, which is a set of real points, contains a positive dimensional semi-algebraic subset. Right? The idea is very simple. So what is the picture? The picture is that you have S downstairs, you have your V inside, which is here, and you look at the universal cover. So this is my bounded symmetric domain X. I have the preimage of V, and I have some fundamental set, which goes to infinity in general. And I have this V. So V is going in a very disgusting way to infinity, because, I mean, this is completely analytic. So I'm making a nice picture, but you have to think that the geometry is very bad near the boundary. This is really what happens. So this is the V. And inside V, I take some guy which is algebraic and maximal. Or this property contains in the pi minus 1 of V. And you have many components, but here I'm just fixing one. So this is my Y here. And now what I'm doing, I'm just looking at all the elements G that will move a little bit my Y. So this will be GY. And I ask that essentially it is still contained in pi minus 1 of V, and it is still cutting this fundamental set. If I can find a positive dimensional semi-algebraic subset of such G, then you see that you would essentially get a one-parameter family of such G. You look at all the translates, and because the action is semi-algebraic, essentially this guy will be algebraic of larger dimension. Okay? But by maximality hypothesis, this means that this subset, sigma of Y, will stabilize Y. Okay? And then I win. So we are reduced to showing that this sigma of Y contains positive dimensional semi-algebraic subset. So what is the main idea of Pila and Zanier following the work of Bombieri-Pila is that even if this map, uniformizing map, is highly transcendental, which it is, I mean, you have to think this is a J function. So it's highly transcendental. One can still control its transcendence if it has nice geometric property. And nice geometric property means that it is definable in some tame topology in the sense of Grothendieck, if you want, or in the sense of logicians, it is defined in some O-minimal structure. So what is a O-minimal structure? So a structure is just a collection of subsets of Rn's that you allow yourself to work with. And what are the properties? Well, the main property is that first you ask that all algebraic subsets of R to the n are definable. Second, you want Boolean properties. So this is a Boolean subalgebra. You can take intersections, etc. You ask that this is stable under product. And what is the strong condition? The strong condition is that you ask this is stable under linear projection. And this is a very, very strong condition, because you have to think that each time you have something dimension n, you go to dimension n plus m by product, for example, and then you reproject. So a priori, you create a lot of mess because of this condition. And in general, you will just do set theory, no geometry. But you will say that the structure is O-minimal if after all these operations, in dimension 1, you get only finite union of points and intervals. And then this means that you are back to geometry. You are not doing set theory, but really geometry. And you will say that a map is definable if its graph is definable. Okay, so why? So notice that semi-algebraic subsets satisfy those properties. I mean, 4 is a classical result in semi-algebraic geometry. But there are more interesting ones. And this is exactly the point of that talk, is that there are non-trivial ominimal structures that do exist. So for example, there is what is called Rn, and this is due to Van den Dries. So what is a definable function in this structure? This is a function will be definable. It is a restriction to some compact guise of a real analytic function defined on some open set of R to the n. So you are allowed to play with all these functions. There is another one where you ask the exponential to be definable, and then you can show that it defines a structure. Be careful here, this is a real exponential. You have no chance, because of the periodicity of the complex exponential, to get something like this for complex exponential. And this is really a trouble. And then what Van den Dries and Miller showed is that you can put those two things together. So you are allowed to work with a real analytic function defined on compact subsets and the real exponential. And this is the one that will be used in all these Dirac-Van problems. Okay, so why is this notion of structure very interesting? I mean, because if you work in an ominimal structure, then there is a way to show that something is algebraic. So how do you do that? This is this fantastic result of Pila and Wilkie that says the following. Suppose you are in R to the m, and you take the subset, any subset, but which is definable in any kind of ominimal structure. Okay? And let's call the algebraic the union. That's what I said. I mean, you give, at the beginning in a structure, you give yourself all the subsets of R to the n that are allowed. And then the function will be definable if its graph is. Okay? So you can either tell which function you want to be definable, but then you have to prove that it satisfies all the axioms before. I mean, usually it will never. Okay? For example, there is no notion of union of two ominimal structures. Usually the union will not be ominimal. This is a remarkable theorem that this is true for analytic function plus the real exponential. Okay? So what is this theorem? It tells you that inside this definable set, you look at the algebraic part, namely the union of all positive dimensional semi-algebraic subsets of this guy. Okay? So this is a subset contained in Z. And then the theorem is that if you look at rational points outside this algebraic part, then there are very few. The growth of rational points of height smaller than t is smaller than any polynomial in t. Yeah, of course. Positive dimensional is crucial. Yeah. Yeah. This is what is the remark. I mean, to get the right definition, you have to understand that you count only positive dimensional thing. Of course, I mean points. Okay. But this is trivial. But in some sense, this is the crux of the definition. That was the key. Yeah. I completely agree. So this is really a remarkable theorem. It tells you that if you are able to count rational points in some definable set, and you show that it grows faster than a polynomial, or at least like a polynomial, then it means that there is a non-trivial algebraic part in it. Okay. So in some sense, from Dirac-Van counting, you come back to geometry.
I mean, you might point out the fill-up of the area paper.
Yeah, so the simplest example is you take a box, 0, 1 times 0, 1, you take any analytic curve in it, and you count rational points in the sense that they are in q bar times q bar. Okay, if you can show that this number of points grows in the height faster, I mean at least like a polynomial, then this curve is algebraic. This is, you can also allow q bar. In fact, I would work with z points, but you could work with q bar. Okay, so we want to work in this setting. And the first step to do that is to prove that this uniformizing map, if you restrict itself to a semi-algebraic fundamental set, then you want to show that this map is definable. In other words, this map, I claim, can be constructed using only restriction to compact subsets of real analytic function plus the exponential. Okay? If you think of the J function, this is an exercise you have to do before I finish the talk, then at the end of the talk, for the J function, this is true. Okay, so this is step 1 in the proof. And for S, so notice first that this is trivial. This is trivial if the Yoshimura variety is compact, because in this case, I mean, after all, you are starting you are starting from a compact fundamental set to a compact manifold. So this is obviously definable in terms of real, in Rn. For S is equal to Ag, it was proven by Peterzin and Starchenko, people from this ominimal stuff, but they use very explicit, intricate computations with theta function. Okay, because in the case of Ag, the uniformizing map is essentially given by theta function. You can just compute. It's difficult. And this is what was used by Pilar and Zimmerman in their proof of Axin demand for Ag. And our proof of this theorem with Ulmo and Yafes is completely general, and it is purely geometric. There is not, essentially there is no computation. It relies only on the structure of the toroidal compactification of the Shimura variety. And this is kind of completely amazing that the geometry of toroidal compactification, in some sense, you have the feeling that it was written for this, so that you see the exponential where they come into the picture. Okay, so, and the corollary that you get from this is that because this map is definable, look at this subset that I was looking for, the set of G in G of R, such that the dimension was equal to dimension. So you are first, you have to realize that dimension is a definable function in any O minimal structure. And so this makes sense, and obviously this will make this subset definable in Rnx because of this result. Okay, so once you are there, what you want to do, you want to show that sigma of y contains a positive dimensional semi-algebraic set. So, well, let's try to apply Pilar-Wilking theorem. You count rational points there. And a miracle occurs in the sense that if you just count rational points, or even better, just z points, you are counting element in G of z, such that when you translate the fundamental domain, you are still cutting the y. This is a very simple set. You just have your algebraic subset upstairs, and you just want to count the number of elements so that when you translate the fundamental domain, you are still cutting it. Okay? So it's just like a basic counting problem. And you want to show this is big. So what is the theorem? The theorem is that, well, you get exactly what you want. Is that if you start from something which is algebraic in your bounded symmetric domain, then there is this constant such that the set of points of height smaller than t in this subset grows at least like a polynomial. Okay. All right. So now let me try to give a few words about the proof of this theorem here, assuming that the map is definable. And then at the end, I will say a few words about the definability. So as I said, you are counting points and using height. So you first have to define the height. And the height, essentially, in this setting, will just, you can take any definition of the height you want, because more or less they are all equivalent. But the point is that you can have tricky powers coming into the picture. And what is nice here is that the way of putting a height on G of Z, you just embed G in GLN, and you take the operator norm. So you see any element of G as being an endomorphism of your vector space, and you take the operator norm. And this would be the nice way of counting things. And then you define the height function as being the max of 1, and then this operator norm. So notice, because I fixed a norm on my vector space that was invariant under the maximal compact subgroup, in fact, this function is defined on the bounded symmetric domain. Okay? And a basic lemma is the following, that in fact, you can compare the height of any element with the norm of any element obtained by translating via this gamma an element in the fundamental domain. In other words, you are in this picture, you have an element G in G of Z, mapping you to such another fundamental domain here, and you want to evaluate the height here. And I'm saying that if you understand this norm infinity of any element here, then you have a natural bound. Okay. So now, how do you proceed? So you want to show that this guy is
there is no logarithm.
No, there is no logarithm. I will come to the logarithm. No, you have exponential growth. Exponential in logarithm is polynomial. No, this is the basic point. Is that? Yes, I will come back to that. But there are logarithms everywhere. But here because you are not taking operator now. This is the main difference. This is exactly the point. So how do we prove that? Well, first thing is that you can assume that you work with a curve. Okay, because any algebraic stuff will contain a curve. So, and if you prove it for a curve, this is fine. So let's do it for a curve. So inside the curve, you will look at all the elements satisfying these properties, that the U infinity, this infinity norm, this operator norm is smaller than T. So you are in the curve. You have your curve upstairs, so you are in the bounded symmetric domain. And now notice that y does not play any role anymore. You just have this, v, sorry. You just have this algebraic guy. So what will be important is that because this is algebraic, this means that this is crossing the boundary of the boundary symmetric domain in a very nice way. There is nothing very bad around the boundary, and this is what will make the difference. And now you have this fundamental domain, okay? And you are trying to count the number of fundamental domains that cut y when you go to infinity, how it grows. So here in this set, I will just look at C of t. So I fix a base point, and I look at C of t. So this will be my C of t, and I will cut it into pieces. So this is C of t. This is a set of elements in y such that this infinity, this operator norm is smaller than t. So let's rewrite this using fundamental domains. Okay. So I just cut this C of t into different, even worse, into different pieces using where the points are. Oops, even worse. Okay. Yeah, it's too many buttons for me. Just sorry for that. So we are here. So you just look at the elements depending in which fundamental domain they are. Okay. So let's imagine that this is C of t. Then here I'm just cutting it depending on how I need the fundamental domain. Let's do a correct picture. For example, the next fundamental domain is here. Okay. I'm just cutting it into pieces. Just making boxes if you want. And now I use the previous lemma. This set of points of operator norm smaller than t, well, I can just say that I look at all the points such that the height of gamma is smaller than bt because of the previous lemma. Okay. So once I'm here, I just take volumes. So the volumes means the volumes for the induced metric on the curve coming from the metric in the boundary symmetric domain of this subset. And then because of this inclusion, it will just be smaller than the sum of all the volume of f intersected with the preimage under gamma of the curve. So now what I'm trying to explain is that rather than counting this, I'm just translating y by element of g of z. So now I have the fundamental domain here. I'm just translating counting the number of elements in g of z such that when I translate back, I'm still getting the fundamental domain. Okay? But I'm allowing only elements of heights smaller than bt. So I get this inequality here. And what is the important fact? The important fact is that this C is an algebraic curve. So it comes from an algebraic curve in the projective space, if you want to complete the C to the end. And now you apply gamma. But this gamma still acts on the compact dual of the symmetric space. So all these curves, they have the same degree. Okay? And so the idea is that because they have the same degree, you want to claim that this Riemannian volume is bounded uniformly only in terms of the degree. And this is what happens. Okay? So this is the following proposition, is that if you take an algebraic curve of the degree d in X, meaning that the Zariski closure in the compact dual is of degree d, then there is a constant such that the volume is just controlled by this degree. And what is surprising is that I thought this lemma was completely trivial. In fact, it's really hard. I mean, it's trivial if the fundamental domain is compact. But the problem is the cusp, because of course you could imagine that the curve is going there. Right? And then you don't understand what happens. The volume could really becomes big. But this is not the case. This is really bounded uniformly in terms of the degree. Okay, but still, I mean, what is important is the uniformity. And this, I mean, it's a delicate computation because you have to make the computation near the boundary. And you already need the theory of compactifications to do that. Okay? So now we are back in the game because I get that the volume of this C of t, well, this is some constant. This is smaller than some constant. And then exactly the guy that I'm interested in. Recall that I want to prove that this is bigger than some polynomial in T. Okay? Because here, I mean, this volume is uniformly bounded, so I just have a counting problem Okay, so the only game that I have to play now is to prove that this is bigger than a polynomial in T. Okay. And, well, what is the lemma? And this is where we are back to the logarithm, is that the logarithm of this operator norm is bounded by the distance. Okay? So now this means that if you take the ball of radius log of T, for the Riemannian metric on the bounded symmetric domain, and you intersect it with C, then it will be contained in my set C of T. Okay. And so what you get is that the number we are looking for is bigger than the volume of the intersection of an algebraic curve with the ball of radius log T. And now this is a classical fact that because you are of negative curvature, I mean, this volume grows exponentially fast. So you have exponential of log T, so you get some polynomial. Okay? And so you get exactly what you want. And well, so this result that the volume of the intersecting, in fact, the curve could be analytic at that point. This is not very important. I mean, the algebraicity was used before. And here this is just, I mean, this is really an estimate in the world of complex Hermitian geometry. Okay, so we get exactly what we want. And so we are done with that proof of Theorem 2. So about the proof of Theorem 1. So Theorem 1 was the fact that this uniformizing map was definable in R and X. In other words, that in some sense, the J function in dimension 1 is definable using only real exponential and restriction to compact things of real analytic functions. So let's look at this case. I will not explain the general case, but let's just try to explain that case. Maybe I will make the picture there. So what we have to do is we want to show that there is a natural fundamental set, which is semi-algebraic in the upper half plane, such that this J function that goes from H to C is constructed only using real exponential function and restriction to compact things of real analytic functions. So what is the classical fundamental set? Well, just look at this circle of radius 1. And then the fundamental set for the action of SL2Z on the upper half plane is a classical picture where you have 1/2 here and minus 1/2. And then the fundamental set is here. So this would be my fundamental set. Okay? So what are the properties of this fundamental set? You have two coordinates, x, the real part of z, and the imaginary part. So the imaginary part is unbounded, but the nice thing is that the real part is bounded between minus 1/2 and 1/2 on this fundamental set. And so now what is the claim? Well, the claim is that you notice that this J function, which is uniformizing, is factorizing through the exponential, the complex exponential. So you map, you already take this h, and you map it by the exponential 2 pi I dot to the disk. Okay. So this is the first thing. But you are not very happy because here this is a complex exponential. But who cares? I mean, the fact is that this complex exponential, of course, you can write it in terms of the imaginary part, which is unbounded, and the real part. The first factor is definable because this is a real exponential, so I'm fine. And here, this is not fine a priori, but this is still fine because the real part is bounded. So this is really the restriction of a real analytic function to a bounded set, so this product will be definable. Okay? So now we are here, and we know that this map is definable, and then we have the factorization of this to C. Well, the remarkable fact is that here, you can just embed D star inside D, and see that this map extends to P1. Okay? So this is a restriction of something defined on a compact neighborhood of. So now, what is the image of the fundamental set that I defined here? Well, this is a compact neighborhood of your big disk, and the fundamental set is something here. In fact, this is really a ball if you replace this fundamental set by a Siegel set like this. Okay? So the image of this fundamental set is this smaller disk where you remove the central point. And what you show is that, in fact, here you have a pole. And it extends to a map to P1C. So this is a restriction to something defined on a compact set, namely the closed disk. And so I win. This is once more definable. Okay. So now this is a very simple-minded picture in dimension 1. And you want to do that in full generality for any Shimura variety. And as I said, I mean, this is the basic picture of toroidal compactification. So you have to prove that for any Shimura variety, you have exactly the same kind of picture for constructing toroidal compactification. Well, and well, this is a classical theory. You just have to go through the details. And it works perfectly well. Well, basically, that's the proof. And I was a bit too fast. I apologize for that. Yeah, exactly. What happens at the boundary, and to prove that everything extends, you really have exactly the same kind of picture. You can write exactly a very similar picture in local coordinates given by the theory of toroidal compactifications. And so everything works the same. Okay, so I guess we'll just stop here.